Then we have to sort of get the values of these terms, okay, and what the values are going to be. Now for this, what we are going to do is we actually need to create another um, page where we write down. So these are the values. Or let me just try to write here. Let me just do it, because otherwise I have to write the whole series again. So let me now try to replace the value of h with some specific values. So let's say h is equal to 1, which means lag 1. Okay, for lag 1 process, lag 1 process, h is equal to 1. So if h is equal to 1, what I get is, here for the first term I get et plus 1. In the second term, h is equal to 1, et minus 1, et plus 1. The third term, I actually get et and et, because the third term, h and minus 1 is cancelling. And the fourth term, again, I get et minus 1 and et. Now, what exactly is going to be the value um, of the all these expectation terms if my h is equal to 1? Now, remember that these error terms are independent, right? So, if they're independent, so let me use a different color. So if they're independent, I can write E of the first term. Let me just write down the first term, Et, and here I have Et plus 1, right? So they're basically two different error terms. Now, since they're IID, I can very well write Et and E of expectation T plus 1, which means what? So they're basically, independent, so that means that's 0, right? Because both of these terms are 0, right? So then the first case for h is equal to 1, I have only one term where my this particular term where I actually see that both the terms are basically et. So basically what it means is uh, cluttering a little bit, but let's just do it here. So it means red, so that it looks very important. Okay, so it is basically going to be, or let me actually use the same red color. It is basically theta and expectation of et square. Simple. Okay. And what is this value of theta sigma expectation et square? Let me just use a page. So let's just go back to the previous color. Theta expectation of et square. It means nothing but what? Theta expectation of et square is what? Theta expectation of et square is my variance square, which means theta sigma square. How do I write this is my variance square? Because I know my sigma square is nothing but, let me use a different color because there's some sort of explanatory note. So because I know my sigma square is nothing but expectation of et square, which is just what it is here. This is just this one, the same thing, right? minus I write expectation of et, to the power whole square, basically this one. Now expectation of et is nothing but 0. This is basically 0. So then it really doesn't make a difference. I can write expression of et square equal to sigma square, right? So that's the value if I have my lag equal to 1. So if for h equal to 1, okay. Now what if my lag is minus 1? If I write h is equal to minus 1, okay, for h is equal to minus 1. So let's just go back and look at the previous derivation, and we'll again come back here. That's here, right? Now in this derivation, now let us put h is equal to minus 1. So first term et and et minus 1, it's 0. Now h is equal to minus 1, so here I will have some value, the second term theta, et minus 1, so I will have et minus 1 square. The third one, h is equal to minus 1, so et and et minus 2. And the fourth term, it is theta square, et minus 1. Again, I have h is equal to minus 1, so et minus 2. So there again, so all these terms will cancel because all they are going to be 0. Only this term is going to be here. Let me use a different color for my h is equal to minus 1 part. So this is the term that is going to be important for h is equal to for h is equal to minus 1. Okay, this is the term which is going to have some value. So let me just write down what that value would be. So okay, for h is equal to minus 1, I can write. So I have seen theta expectation of e t minus 1 whole square. Okay, so again, likewise, it doesn't make a difference if it is et or et minus 1, all are sigma square. I can write theta sigma square. The last part. So these are clear. H is equal to 1, h is equal to minus 1. We get the covariance value theta sigma square. Now the last part is where I put h is equal to 0. Okay, h is equal to 0. That means there is no covariance at all. So I'm basically considering the same period value, right? So I'm not actually taking a last period average. I'm taking the same period average, basically, to say. Okay, and if that is the case, what I get is, let us go back to the previous page. Okay, so here what I want to write is, I want to write h is equal to 0 because I'm not introducing any lag anymore. I'm using the same value, et, with a weight. Okay, so if that is the case, then I will have my first term is going to be et square, which is clear. The second term is going to get vanished. The third term, h is equal to 0, is going to be 0. Fourth term, h is equal to 0 means I have another variance term, right? So et minus 1 square. So that means if I use h is equal to 0, let me use another color. Okay? If I use h is equal to 0, so these terms are going to contribute to our covariance. Okay, these terms are going to contribute to our covariance. H is equal to 0. Here also, if h is equal to 0, this is going to contribute to our covariance. H is equal to 0. Okay. So if that is, so what I'll get is, here I'm going to get a sigma square, and here I'm theta square and sigma square, right? So what I'm going to get finally is, so let's write it. For h is equal to 0, I can write this value is going to be sigma square plus theta square sigma square, which means that I can just simply take a sigma square and 1 plus theta square. Okay, so now you see in all the terms of covariance terms, we see that there is no presence of any t. So what that basically means that, and also we have seen the expectation to be constant and the variance to be constant. So that, which basically means that the MA1 process, what that we have is a stationary process.